Anyway, welcome to Chem 112. We're going to begin the class by starting with some things that you will probably find to be familiar. That is, the three states of matter. Now, in Chem 111, you dealt with gases. And so that may have been one of the last things you covered, depending on when you took Chem 111. Some of you, I know, it's been a while. And so so there's some things we learned about gases, and I think you're familiar with them. A gas as low density, it takes whatever the shape of its container is. That's what it means by indefinite. And whatever the volume is, it will actually expand to fill the volume. And then we have this thing called intermolecular forces of attraction, which is going to be largely what this is going to, this chapter and this stuff we're covering. A lot of it will focus on what that means, intermolecular forces of attraction. For now, let's just say they're the forces that hold molecules and atoms together. And in the case of gases, they're pretty much close, especially an ideal gas, they're non-existent. But in real gases, sometimes there may be some weak interactions. Liquids, they have a much higher density. They have an indefinite shape in that when you pour, you pour into a different glass, a different shape, it will take that shape. But the volume does not change. The molecules that make up that liquid don't expand by just changing its container. So the volume's definite, and that's because the forces that hold the molecules together are a lot stronger than they are for a gas. And so we'd say they're moderate. They're strong enough to hold it in place, but not so strong that they do what a solid does, which has a very high density, just like liquids. They have a definite shape. In other words, if you have a solid block like you're looking at here, that solid block will hold its shape regardless of its container. So it's got a definite shape, and therefore also a definite volume. And the reason why there's a definite shape is because the intermolecular forces of attraction that hold it together are very strong. So let's continue and talk more specifically about each of the phases. So in the case of gases, again, this should be relatively review for you, because you've had this in Chem 111 or whatever your version of college chemistry 1 is. And the gases are always moving around, so they're buzzing all over the place. They are not held together, and in the case of a ideal gas at all. But in some real gas situations, when the pressure's high enough and under the right conditions, they do see each other and have some weak attractions. But for the most part, we can treat gases as though there are no real intermolecular forces of attraction, because of the fact that they're always moving and they're held together very little or not at all. They can expand then to fill whatever the containers are, because they're buzzing around moving. So they expand. There's lots of space between the molecules. That's why they have a very low density. And because of that, there's space to squish them into, so they're highly compressible. So now we can go on and kind of compare what we just said about gases to liquids. The liquid molecules are packed closer together, and that's because there are forces of attraction that hold them close together. They see each other and they're held together, and they touch each other. They have very limited movement because they're held together. Now they can move. They move more than a solid and much less than a gas. They can definitely take the shape of the container because the forces that hold them together allow them to spread out, but not allow them to break away to expand like a gas does. So that's why we say the volume's not changed, but the shape can. And they're not really compressible because there's no space between the molecules to squeeze them in. So when we look at solids now, we can see that they're very closely packed. They're not necessarily, in some cases, they're not more closely packed than the liquid form. Water is a great example of that. In fact, water is its most dense at 4 degrees Celsius, which it is a liquid, and then it expands a little bit more because of the way that the water molecules arrange, takes up a little more space than in that liquid form. So as we look around here, then we can say then that we can't necessarily say there's more density between the two, but we can say that there's a high density for both of liquid and solid. So it's very closely packed, but in this case, they do not move. They don't flow. Water, liquids flow. The solids, they're held in place, have very fixed positions. They vibrate. They wiggle. Wiggle, 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 wiggle. And so we call that vibration. And so the molecules are moving, but they're not really moving in an XYZ plane. In other words, they're not translational movements. They're vibrational. They're just vibrating. And so every solid that you see and touch and hold is vibrating. It just very at the molecular level, and you don't even notice it because that's a very subtle thing. We can measure those vibrations using certain instrumentations, but that's about it, though. We can't really experience it with our own senses. Because they're so held together and they have fixed positions, that's why they retain their shape and volume, and that's because the forces of attraction that hold the molecules together, as I mentioned in that table, much higher. And of course, since these molecules really are tightly arranged, there is no free space to compress. Now, when thinking about solids, we definitely can think about other aspects of solids. So solids, pretty much you can classify them as crystalline or as amorphous, okay? Now, crystalline means that you have a very regular, I'll say that, it's a regular geometric pattern that's followed. So you can see that if you look here, you have these things that are positioned in a very regular, predictable pattern. And of course, table salt, sodium chloride, sugar, diamonds, some types of metals, other things can have a crystalline pattern. Amorphous means that they're randomly distributed. They're in a fixed position, but you can't predict the position by looking at the pattern of where you'll find them. And so that's what amorphous is. Something like plastic or glass would fall into that category. So why does a particular state of matter exist? Why is it that solids are solids and liquids are liquids, and that when you change the temperature, it changes the phase of matter? You take some ice, you add some heat, and it melts it. And then you keep heating it up, and eventually that liquid turns in to a gas. So it boils and evaporates. So what is it that dictates that? Well, a lot of that can be explained by looking at the kinetic molecular theory. Whether something's a solid, a liquid, or a gas depends on two things: the kinetic energy in that system and how strong the forces of attraction are that hold those molecules or atoms together. When the kinetic energy is low enough so that the forces of attraction can be felt by the molecules and atoms, they'll be in a more condensed phase, liquid, gas. When kinetic energy is significantly higher than the forces of attraction that hold them together, the molecules together, then they'll be in a less condensed phase. So if something were solid, it would become less condensed. It could turn into a liquid or even to a gas. So the state of matter then depends on the amount of kinetic energy in that system and the forces of attraction that are holding atoms and molecules together. Applying that then, so kinetic energy tells us that the higher the kinetic energy, the more movement the molecules will have, the more force of movement they're going to have. They're going to be moving all over the place. And the less kinetic energy is just the opposite. So, for gases, the kinetic energy is more than enough for atoms and molecules to break free from the forces of attraction. That's why they're very mobile. They can fly all over the place because they're not being held together as well. And the kinetic energy is such that they way overcome any forces of attraction that could be there. That's why they're a gas. In liquids, the kinetic energy, Ke, that's what I mean by kinetic energy, is high enough to break free from some of the forces of attraction, but not all of them. So there's limited mobility. They're still being held together, but not as strong though of interactions as a solid. When kinetic energy is significantly low compared to the forces of attraction, the molecules will have extremely limited mobility. They'll be held together really well, and all you really be able to see are molecular vibrations. And so I want you to see this. There's a simulation I want you to see, and I'm going to break away to that now. And in that simulation, you'll see how you have the kind of the battle, kinetic energy versus the forces of attraction. And you'll see how those two things go hand in hand. Now I'll say I'm going to use a program that I found on a website that simulates this, and it's not a perfect simulation. It's only looking at a population of molecules and not every molecule in the system that we're looking at. So it will look like, for instance, it'll look like there's more space between the molecules in the liquid and the solid than there normally would be, but that's only because they're focusing on the behavior of just a small group of these molecules. And so in the molecules you'll see in this video are molecules of water. So I'm going to let you see that now. I think it's actually pretty useful and to help you to picture it. Okay, I want to do a simulation with you. This is a program, a website that I found that allows us to do simulations. I want to draw your attention over here. Here is a graph. This is known as a heating curve. We're going to do these later on, and in fact, you're going to see the heating curve. We're going to look at something that looks just like this, and we'll be able to do some calculations to figure out how much heat it would take to take a substance from one temperature to another temperature. I'm not going to get into this a lot right at this moment. What I instead want to do is draw your attention to this glass of ice. Right now you can see through here the reds, little dots that you see, those are oxygens, and the white dots are hydrogens, and they're vibrating. Hopefully you can see how they're vibrating here. That's what I mentioned about the movements you'd see in a solid. The best they can do is vibrate. They don't go bouncing all over the place, and they're held together with very strong forces of attraction compared to the kinetic energy that's in the molecules. So there's not enough kinetic energy to break free from the forces of attraction. So all it takes is some heat. So I'm going to allow this thing to go from minus 50 up to like 150 degrees, and we're going to watch what happens as these things go. So we're starting as a solid. The only movement you're going to see is vibrations. So let's let this warm up. So I'll start it. You can see how the temperature changes here, and take a look at what's happening here, and then you can also trace what's going on here.
So here we go. We're moving up. The solid is gaining heat, and now it's starting to melt. And I want to show you something. I'm going to stop right here. I want you to notice that during melting, on a melting curve, the temperature during the phase change, this flat part is the phase change, the temperature does not change. All of the heat is going into causing the solid to melt. All the heat is going into breaking apart these intermolecular forces of attraction. Once the melting is completely done, all you have left is water, liquid in this case. This is H2O, by the way, in case you didn't pick that up. Like I said, reds are oxygen, whites are hydrogen, so you can see little molecules of H2O roaming around here. All right, we're at 0 degrees. We're going to let this finish melting. Okay, it's starting, and as you add heat, the molecules are going to now we got a liquid, and every now and then there's enough energy to free up one of the liquids away from the liquid phase, and it turns into a gas. That's what evaporation is, right? That's where liquid turns into a gas. But as the temperature is increasing, the molecules are moving much more kinetic energy, and with better able to break free of all of the interactions that are holding them together. So that's what's happening here. Now we're going to boil. We're starting a phase change. During phase changes, again, temperature doesn't change. All of the heat is going into phase change and not into kinetic energy. So now we're at a fixed kinetic energy here. The temperature isn't changing because there's enough kinetic energy to just blow all these things into the new phase. Now we'll go backwards. I think that would be fun. So let's go backwards. So this is supposed to represent a bunch of gas particles floating around, bouncing all over the place, going crazy. Let's see how this goes. So the temperature's dropping, the kinetic energy is lowering, and now we get condensation. And the molecules start holding on to each other. They're attracted to each other. Again, this is just an approximation. There is no space between these molecules. They're all touching each other at this point. But this is just trying to show, imagine all this liquid has a bunch of more molecules. This is just showing a small population of them, a sampling. Now they're slowing way down because the temperature is going down. Kinetic energy is going down. And the forces of attraction holding them together can begin to form. And now we can get crystallization and ice. And the vibrations now are the only movements you can see. So this simulation is meant to show kind of what's happening at the molecular level, at least to a small population of molecules.
So one of the things I hope you noticed from that video was that as the temperature is increased, the molecules moved with more energy. They moved at a more rapid state. The vibrations in the solids increased. The molecular motions of the molecules in the liquid went faster as the temperature increased. They had more energy. They move more rapidly. And then, of course, as a gas, they just blow right out of there. So I want to look at kinetic energy a little bit more. There clearly is a connection between kinetic energy and temperature. That's what you saw in that simulation. You lower the temperature, the molecular movements lowered. That's because the average kinetic energy lowered. Okay, so there is a relationship. Kinetic energy is proportional to the temperature, and that proportionality is met by this here. K is a constant, and so it's 3 halves times K. And it doesn't really matter to me that you know what K is and all that. The point is, I just want you to see that there is a direct relationship between K, the kinetic energy, I should say, and the temperature. And that proportionality is described by 3 halves K. So a measure of kinetic energy, you could say then, is temperature. The higher the temperature, the higher the kinetic energy, and vice versa. The lower the temperature, the lower the kinetic energy. So when you increase the temperature enough so that the kinetic energy is high enough, it can begin to overcome the attractive forces that are holding the molecules together. Now, what are these attractive forces? Well, generally they fit into what are known as electrostatic forces. Okay? Electrostatic forces are the measure of force between, say, a positive and a negatively charged substance. So that could be, you know, a cation attracted to an anion. They see each other and there's a force of attraction. And so the strength of these forces can vary depending on the magnitudes of these charges. Sometimes we are dealing in formal charges, and sometimes we deal in what we call a partial charge. A partial charge occurs, so I'll call it. We'll touch on this in a little bit, but I'm just kind of giving you some foreshadowing. Whoops, not particle, partial. Sorry about that. I don't know why I get all excited about these things. Partial charge. And so they're not quite like a plus one. They're just a case where, let's say that this circle represents electron cloud. That's our electron cloud. And remember, electrons are negatively charged. Okay? So a way that we get a partial charge are when the electron cloud is distorted so that you have some extra electrons on one side, and that will give what we call a partial negative charge, and that's a partial positive charge. So sometimes you can have molecules having these partial charges because you have an unequal distribution of electron density on one side of the molecule compared to the other, so it creates an excess of electrons on one side and a deficiency on the other, and that's where we get the partial positive and partial negative charges. So just like negatives charges and positive charges, like ions can attract, positive partial charges can be attracted to negative partial charges in the same way. So that's what we mean by electrostatic forces of attraction. It's the attraction between those forces. Between those charges. And that attractive force can vary depending on how big the charges are and how close the species are together. That's defined by something called Coulomb's law. The strength of the attractive forces depends on the kinds of particles. That's something I just mentioned. So if you have stronger attractive forces, they're going to resist movement better. So that's why some interactions will require higher temperatures and higher degrees of kinetic energy to break free from the interaction. So you could say then that really, if you think about it, kinetic energy opposes the attractive forces that hold the molecules together. Higher kinetic energy will give the molecules more energy to break free from one another and to potentially make a phase change, for instance. So that's kind of the deal here. This is kind of how we use kinetic molecular theory to describe the phases. Now, I just want to mention, this is a little caveat, I mentioned this before. The only time anything lacks particle motion, vibrations and all that, is at absolute zero, where there is no motion. Above absolute zero, then particles are moving, at least vibrating. Some of them can do what they call translational and rotational motions. That's something for a physical chemistry class beyond the scope of this class. But the point is, molecules can move around or they can vibrate, but they're always moving unless they're at absolute zero. So this is kind of a summary slide, but I want to bring things together, and that's why I want you to get this. Okay? So the forces of attraction between molecules are fixed. Okay? They're not going to change because you change the temperature of the kinetic energy. They have a fixed amount of attractive force, and so some particles have higher attractive forces, I just mentioned that, and some have lower. So for instance, if you had a particle that had a +2 charge connecting with a particle that has a -1 charge, that will be a stronger force of attraction than if you have a particle that has a +1 charge and a -1 charge. There's just bigger charges will lead to bigger charge differences, I should say, will lead to stronger forces of attraction. So if you have a substance that has really high level forces of attraction, one example is the one I've already given, water. Okay, so you got water. Water is capable of binding with other waters with very high attractive forces. And we'll talk about those later. It's called hydrogen bonding, but we'll talk about it later. Then there's other molecules, like I'll say propane. Propane is CH3, CH2, CH3. That's propane. And propane actually is not held together by very many strong forces of attraction. There's not much holding one molecule of propane next to another molecule of propane. That's why at room temperature, water, for instance, is a liquid, because the forces that hold it together are strong enough to keep it together at room temperature. But at room temperature, propane, which is weakly held together, one propane molecule, I'll draw not so so if we have two propane molecules and then we look at the forces of attraction that hold them together, we're going to find out that they're very weak. So they don't see each other with the same force of attraction as two water molecules. So that's why at room temperature they're a gas, because they're not able to hold each other close enough together to withstand the kinetic energy at room temperature. So that the kinetic energy is enough at room temperature to break apart liquid propane, but it's not strong enough to break apart liquid water. Okay? So when you add enough heat, though, water eventually breaks apart too. When I say breaks apart, I mean water molecules no longer are attracted to each other, and that's why they boil and float off as steam. And when you add enough temperature, you add enough kinetic energy to break those interactions, those forces of attraction. Okay, so so the stronger attractive forces for boiling, the higher you're going to need to raise the temperature to create enough kinetic energy to overwhelm those stronger forces. And same thing with gases. If you can get the gases to the point where you lower the temperature enough, when the molecules see each other, if they have a stronger force of attraction, they're going to condense at a higher temperature than those that have really weak forces of attraction. So if we look at this little molecule, this little diagram then, so we add heat, we go from this highly ordered structure to a less ordered but ordered. This is not nearly as ordered. Liquids aren't nearly as ordered as solids, but with the added heat, there's more kinetic energy. They bounce around more, so they aren't as held as tightly. And then as we add more heat, we can just completely overwhelm the forces of attraction holding them together. And just like I showed you in my little simulation, we can cool down the gas, and the gas begins to slow down, the gas particles slow down, and eventually they start bumping into each other and sticking when the forces of attraction are strong enough to overwhelm the kinetic energy of the system at that temperature. And if you keep lowering it down, you can get even more order as these molecules, their movements get slower and slower, so that the forces of attraction that hold them together are not impacted so much by the kinetic energy of that system. They're stronger than the energy that makes them want to break free. They hold them together instead. So that's the end of part 1 of this video.